Okay, this is the final talk of today's meeting. It's a pleasure to introduce Frank Trujillo, who's going to speak on the Hausdorff dimension of invariant measures of AIETs. Over to you, Frank.
Okay, thank you. Thank you very much for the invitation, and thank you for the previous talks. It was very nice. So I'm very happy to be here, but I'm a bit afraid because I come mostly from dynamical system setting. So I feel a bit like an outsider, but I hope I will be able to make myself understood here. So I'm going to speak about the Hausdorff dimension of a particular dynamical system I'm interested in, which is affine interval exchange maps. So this is a joint work with Przemek Berg, Krzysztof Franczek, and Łukasz Kotlewski, all from the University of Toruń in Poland. So just to begin, I want to introduce the particular object I'm interested in, which is affine interval exchange maps. So maybe I will start with a picture so that things look easier. So what is an affine interval exchange map? So it's a bijection of the interval. So I want my F to be a bijection, which is piecewise linear. So piecewise linear map that has a finite number of discontinuities. And if you want to be really picky, you can assume that this is right continuous. This is not very important, but just for these things to be well defined. So basically it's just something that looks like this. So I will try to motivate in a second why I'm interested in these transformations, but just I want to give you a few facts about these transformations. So let me say a few facts is that if you assume that these maps, if you pick one of these maps without periodic points, so if I pick a map without periodic points, AIT without periodic points, in general, so I'm trying to avoid here explaining what is particularly this generality. So under quite general conditions. So if you're interested later, I can try to discuss a little bit more what I mean by this. But what I want to tell you is that in general, these maps will be uniquely ergodic. So these maps are uniquely ergodic. So what do I mean by this? It means that I have an unique invariant measure. So this means that I can find there exists a unique invariant probability measure, which I will denote by mu f. So this is simply to say that this measure is preserved by my system. Okay, and it's about this measure that I want to talk about today. It's basically I want to know the Hausdorff dimension because actually in general, so second property about these maps, in general this transformation will be orthogonal with respect to the Lebesgue measure. Okay. So my goal of today is to study the following. So I want to say what is the value of the Hausdorff dimension of this measure. Okay, so I think I don't need to say this, but just in case, just to recall, the Hausdorff dimension of a measure is defined as follows: it's just the infimum of the Hausdorff dimension of all the sets of full measure. Okay, so just a little bit to motivate this further, I'm interested in this measure and why, in this Hausdorff dimension. When you have a system, so the systems I will consider today, they will be minimal. So if you have, if I have an IT that is minimal, then for every point that I pick in my space, so for any point that I pick, when I take this kind of averages of measures, so if I take this kind of measures, so delta on the point. So here I'm denoting by this the delta, the Dirac measure on this particular point. Well, it turns out that in this case, since I'm uniquely ergodic, I am converging to this particular measure. So meaning that when I look at the iterates of any point, this is actually dense in my system, but there is a very particular way they're distributing. And this measure is somehow encoding the way they're distributing. It's like some fine statistical information on the orbit of this. So if this dimension, for example, is smaller than 1, it means that although my orbit is minimal, I am somehow accumulating more and more in a very small set. So it's, let's say, from the dynamical systems point of view, is quite interesting. And so this will be my goal today. So I didn't say it, but please, if there are any questions, please do not hesitate to ask or interrupt. Be very happy to give more explanations. So these are the systems I'm interested in, but okay, why this particular kind of system? So let me give a bit more of motivation. So a bit of motivation. Why do I consider these systems? Well, there are several reasons. So the first reason is that the affine interval exchange maps, so the AIETs, they appear, they are like, they are linear, okay, affine model. Actually, you can think of this as some kind of toy model for the so-called generalized interval exchange maps. So these are just a more general version of what I'm studying. So it's basically, sorry, this is not very pretty. I think I cannot make it prettier. Okay, we'll just steal this. Put it here. So this will be just a map that instead of looking like this, I will put something that is a piecewise diffeomorphism. So something like this, something like this, something like this. I don't know, this one looked like what? I was much. Okay, so these are simply, I'm changing to be affine to be a piecewise diffeomorphism. And it turns out that this kind of transformation, they appear as first return maps of flows on surfaces. Okay. More precisely of area preserving flows on compact surfaces. So in many situations, this kind of map, this generalized interval exchange map, they are C1 conjugated to affine interval exchange transformation. So basically understanding more or less the affine case, which is usually easier, allows us to understand the more general case. Second motivation, if you know what a dilation surface is, because I'm going to define it, AIETs are exactly first return maps in dilation surfaces. So second thing, and the third motivation, you can just see these transformations as generalizations of piecewise linear circle maps. Okay, so there are plenty of reasons to consider these maps. So just before giving you a precise statement of what I want to show you today, let me just tell you about the previous results, which actually are not that many, so I can go quickly on this. So there's a very well-developed theory for circle diffuse. So we know a lot about the Hausdorff dimension if you consider a circle diffeomorphism. So I'm not going to give all the details, but this is very well known. But besides the case of a piecewise linear circle map, where we have basically two cases. So the Hausdorff dimension is in general. So it's 0 typically, let's say, again, in this typical sense that I don't really want to define. And you have examples where the dimension is positive. We have some examples. But basically, this is all what we know. We don't know much more about it. Okay, so what I want to tell you about today, which actually my plan is not working because I was supposed to be using this for later. So I want to tell you about the following. So my goal today is to tell you this. So theorem with Berg, Janšek, Kotlevsky, and myself is to tell you that for a very particular scenario, because sadly I don't know how to do it in the general case, so for so-called self-similar affine interval exchange transformations, I can tell you that the Hausdorff dimension is strictly positive and strictly smaller than 1, and actually we have an explicit formula for it. So there is an explicit computable formula, which I don't want to write because it's actually not very pretty and very long. But the point is that we have something that is computable. So you give me an affine IT with certain parameters, I don't know, lengths, slopes, and I can give you the exact Hausdorff dimension if I assume that this is self-similar. So I will start by defining what self-similar is, which is actually not too difficult. So I prepared some pictures for this. So too big. So I want to give you a definition of what self-similar is. So self-similar. So in general, an affine IT. So an affine IT is something that looks like this. So I take something from 0, 1. I have some intervals, which are the intervals of continuity of my transformation. And my transformation is simply exchanging the order of these intervals and changing the lengths. So basically, I just try to draw a picture here of what is going to happen. And actually, I will take this. And when I will say that my transformation is self-similar, well, if I can say that I can find some small value, so I will say that f is self-similar if I can find some value smaller than 1, such that the induced transformation, so I will explain in a second what I mean by induced transformation. If the induced transformation is basically after rescaling the transformation f. So I will just take a small interval, I will induce my map, and I will recover basically the same transformation. So by this, I just mean that I can recover my map as follows. I can say that f of x is equal to 1 over sigma of f induced of sigma x. So what is the induced transformation? So it's something quite common in dynamical systems. I'm just taking a sub-interval, so a part of my space, and I define the transformation as follows. So I take a point, and I will define it as the first iterate of my point. So maybe let me give the domain to be more explicit. I'm just defining this as follows. I say that this is the iterate, the first iterate that falls back in the interval I started. So this is this, where R of x I define as the first return to my set. So for affine interval exchange maps, one can actually show that whatever interval that you pick, you will end up with an affine interval exchange map. And in my case, I will say that I'm self-similar. So I'm trying to define this. I'm saying that I'm self-similar if when I induce in this particular sub-interval, I basically find again my initial transformation, but somehow shrinked. Okay. So why I'm saying things like this? Because when one works with interval exchange maps or affine or generalized case, one relies a lot in renormalization. But I don't want to define the renormalization here. But basically, this is just an instance of renormalization and being self-similar. So for those of you that might be more familiar with the theory of renormalization, being self-similar is simply saying that self-similar is the same as saying that f is a periodic point for the so-called Rosevich renormalization. Okay, I don't want to enter into details here, but this is just to say that this is the class that I'm going to focus on. Why is it better for me and for what is easier to work? Because as I was saying, most of the tools that we use will be based on renormalization, and the fact that you're a fixed point of renormalization makes things much more easier to study. Okay, many things will tend to repeat, and it will be easier to analyze. So I just wanted to avoid defining other normalization. I thought it might be clearer for the talk. So I go back to the result. Basically, I'm just saying that if my affinity is subsimilar, then I can compute explicitly its Hausdorff dimension. Okay. Is it more or less clear what we want to do? Are there any questions? Okay. So I will try to explain a little bit how do I calculate this? How can we calculate this? But again, the tools will be more dynamical, so I will try to just give at least the flavor of what the proof will look like. And for this, I will need to explain a little bit more, okay, how will I exploit the fact that this happens, that I am self-similar and I have this kind of transformation. Okay, so I'm actually then going to, I don't know if I can add a page here because I need, yes, one more page. And I will just copy this and try to be a bit more clear about what I want to do here. So how can I exploit the self-similarity? What does it mean for something to be self-similar? So usually one uses renormalization to, let's say zoom in into dynamics. And when I'm going to zoom into my dynamics, this allows me to see my space in a different way. So basically, I want to show you what is happening. So for an affinity, at the beginning when I start, I am basically saying that, let me move this a bit below. I start with an interval 0, 1, which is naturally split in these intervals. In the intervals that are here on top. So this one, this one, this one. So let me suppose that I have the intervals. One, I am self-similar, so something like this. I have also a description for this smaller interval, which here I called ij with some superscript. And since I'm self-similar, I'm just actually shrinking my space. So I'm just saying I will contract by a factor sigma, which means that the length of these intervals is just multiplying the initial length by sigma. Okay, I'm just rescaling. That's the only thing I'm doing. But once I have this, I also have a different way to see my whole space 0, 1. It turns out that you can see this as a bunch of Rocklin towers. So basically, I can take these intervals that I have here, and I can iterate them a certain amount of times. And these iterates will provide me with the full space. So what am I doing here? Maybe let me put this down. If I am to draw the whole space here, so if I go back to 0, 1, then what's happening when I take, for example, this interval here, this blue one? Well, when I make an iterate of this interval will probably go over here. Some further iterate might go over here. They don't need to have the same length. It goes around. So basically, I'm saying this will be f of this third interval. This will be second iteration. I have some other iterations. And finally, after a few iterations, I go back here. So let me say that this was f3 of this interval. This is f4 of the interval. And then this interval, when I iterate, I go back to my initial interval. So I find this interval here, which is the last iterate, f5 of I3. And the same will happen with all the other intervals. So basically, I am just saying that some intervals, for example, of this yellow interval will appear over here, will go, and then they go down. The same will happen with the red one, red. We have some distribution somewhere. And the same will happen to the green one. So the green will fill some of the remaining gaps. And basically, if I was to put these intervals, let me say I will put the blue intervals. I can represent them as the iterates here. So say some intervals are bigger, smaller. And I can see my whole space basically as just iterates of these basic intervals that I have here. Okay. Again, when I iterate, they are changing lengths because I have an affine, so affine AT. So I'm just multiplying by some slope. But then if you allow me to say, okay, let me draw them, all of them with the same length for a second, just for making the picture nicer. If I have 1, 2, 3, 4, 5. I have some iterates of the green one, some of the red, some of the yellow. I can see my whole space as just these Rohin towers. So here I'm cheating a little bit because, again, in reality, all of them have different lengths. But if you want, you can think of this picture are looking this through a lens, so the lens of the invariant measure. So this is just through the invariant measure lens, glasses, let me say. All of them have the same invariant measure because they are just iterates of the same interval, right? The blue ones, all of them are iterates of the blue one, of the initial blue, so all of them have the same invariant measure. And once I have this, you see, I made this induction once, but I could, for example, in theory, I could simply say, okay, consider the induced map not to 0 sigma, but to some iterate. And again, the fact of being self-similar means that if I rescale at some smaller scale, this picture tends to repeat. Okay? So all of these intervals and partitions define something that we call dynamical partitions. So basically, what I'm saying is I can think of these intervals, the initial one, I1, I2, I3, and I4, as my initial dynamical partition, P0. And then I can think of this thing here as my first dynamical partition, P1. And if I was to induce into this interval, I will get some intervals, some base intervals, so we'll get something very small here. Some intervals, I will get some other dynamical partitions. So let me say that doing this procedure, you define a sequence of dynamical partitions. So inducing on this kind of interval, one can produce a sequence of partitions, which we call dynamical partitions. Okay, again, all of this, it's easier to see through our normalization lens, but it's a bit difficult to define it in less than 20 minutes. So I had the picture here prepared that it was prettier, but this will be for later. So just let me say what are we going to do with this? So what I will do with these dynamical partitions, so if I want to calculate the Hausdorff dimension, I will use something that it's very well known, which is called the Frossman lemma, which simply says that if I have a Borel measure, let's say 0, 1, and if I know that the lim inf of this kind of quantities, log of epsilon, if I know that I can bound this for almost every point, so for mu almost every point, then I know that my Hausdorff dimension, okay, the dimension of my measure, is between these two values. Okay. But again, this is a classical result, but estimating this kind of limit is a bit hard because, okay, I have to take a point and I have to take any intervals around. But here's where I want to use these dynamical partitions. So all of this is to say that the dynamical partitions come in handy. So it's possible to show in this setting that for a self-similar IT, I can show that this value, this lower limit given by the Frossman lemma, corresponds to the following, corresponds to the limit when this goes to infinity of the log of what I will denote Pn of x, so mu f of this, over log of the Lebesgue measure of this, where I denote by Pn of x is the unique element in my partition that contains x. Okay, so I'm just saying that these dynamical partitions will allow me to reduce everything to calculate things restricted to this dynamical partition. Okay, this is the outcome of all of this. And why is it good to work with self-similar? So I will not be able to talk much about this particular one, Lebesgue, but then just let me try to justify how you can calculate this using dynamical partitions. So as I was saying, all of the elements in the dynamical partition, let's say in P1, they are iterates of one of these basic intervals. Okay, so basically, this is an element of the dynamical partition, and this is an iterate of this particular interval. So when I take a quantity like this one, mu f of p n of x, what I know is that this one is the measure of some iterate of some fundamental interval of this kind. So here I'm trying to denote by this the intervals that will be exchanged by rescaling at the scale sigma n. But again, I'm just rescaling a scale sigma n, which means that I am just taking sigma n of the initial one. And from this, one can easily see that if you take the logarithm and you divide by n, well, this is a particular value. I don't really care what is the value because it will disappear. And I can tell you that it will be exactly equal to sigma. And okay, if you want to calculate this other one, log of Leb, it's way harder. So what we did was to associate to this kind of transformation some kind of Markov chain and try to estimate it using some Markov chain, but I will not have the time to explain here. But basically, the magic is that when you consider self-similar, many things simplify. And we are allowed to do something like this proposition. Okay, so let me just mention that, okay, I didn't have the time to tell you much more, but our work is much more general than this. I was just trying to give a toy model with this example, but we are working also with transformations that are not exactly self-similar, but self-similar-like. So we can obtain much more general results. But I think that's all I wanted to tell you today, so I don't want to go much over time. Thank you.